Hello, this is Jared Bryan. I'm going to talk about one of the most important ways we learn about rocks in the subsurface. That's with borehole geophysics. Before launching into rocks in the subsurface, let's look back at some of the descriptions you made of rocks or landscapes from earlier in the week. And just think about what sorts of things you looked for. If you had to describe the rock pictured here, what sorts of things would you have said? Well, you probably would have mentioned things like the different colors, the shapes and sizes of the grains. You might have tried to identify the minerals. If you're looking at a landscape, you might look for bedding or faults and folds. But all of these observations rely on things you can see or feel. These observations are really only accessible to you if you can hold the rock in your hand. But most of the rocks on Earth are not visible at the surface at all. You can't see them, you can't feel them, but it's still very important that we're able to describe them. So the question is, how on earth can you make these descriptions? For the most part, we describe rocks in the subsurface using a different set of senses given by various different geophysical methods. For example, we might use seismic methods, where we track the time it takes for seismic waves to travel through different rock types. We might look at how the surface of the Earth deforms as a way of inferring deformation below the surface, or we might use observations of the electrical and magnetic properties of the rocks to infer rock and fluid properties. But these non-bold terms are, for the most part, made from the surface of the Earth or even from satellites in space. But another thing we can do, if we really want to drill down on the actual fine-scale properties of the rocks in the subsurface, is to literally drill a hole and measure them from the borehole. And in all these cases, what we're really doing is substituting the familiar observations we might make with our five senses with some other measurement of the rock's physical properties. Things like seismic wave velocities or densities or electrical resistivities. But why should we choose to drill a borehole at all? It's quite expensive to drill a really deep hole, so what's the value added by a borehole relative to some of the other easier observations you can make from the surface, like seismic wave velocities? Well, the real benefit of a borehole is that we can observe the rocks in their natural environment, right? And this happens in two main ways. The first is through wireline logs, where we send some tools down the borehole to measure the physical properties of the rocks around the borehole. And the second is to haul some cylindrical section of the rocks back up the borehole so you can study the actual rocks. We'll focus here on the wireline logs and begin by walking through some of the common examples of wireline logs, or geophysical logs, commonly collected in a borehole. One common geophysical log is the sonic log, or acoustic log, which works in much the same way as observations of seismic waves on the surface. We lower a tool down the borehole, which emits some sound pulse, which is an elastic wave, and measure the time that it takes to travel from the source of the sound wave to some receiver. We can learn a lot about the rocks, actually, by measuring these travel times. We know that velocity is a distance over time, right? Miles per hour. And rearranging this, we can find that delta t, the travel time, is equal to the distance between the source and receiver divided by the velocity of the sound wave in the rocks. And we know that this is dependent on the density of the rocks and the stiffness of those rocks, which you can recall from our last video on deformation. So we can use these observations of travel times to get at things like the density and elastic properties of the rock and things like porosity, or empty space in the rock. Another type of log we can use depends on the electrical properties of the borehole. Self-potential measures the natural differences in electrical potential through the borehole. We put one probe at the surface, which is at some fixed electrical potential, and then lower another probe down the hole. The electrical potential difference encountered in the hole is due to two main different signals. We have electrokinetic signals, where water flows over some naturally charged rocks, and electrochemical signals, where we look at the electrical interactions between the drilling mud, which is used to maintain the stability of the borehole, and the fluids found in the formation naturally. Because those fluids in the formation affect the electrical potential we record, we can use the self-potential log to learn about the permeability of the rocks and composition of the fluids. We can also use the self-potential log to learn about the amount of shale or muddiness of the borehole. Another electrical log uses an active source of electricity rather than measuring natural differences in electrical potential to find how much a formation resists the flow of electricity. Usually this is used as an indicator of fluid presence and therefore porosity, and permeability, and as an indicator of different rock types. For example, shales are usually low resistivity because they're closely linked with clays, which usually have lots of free charge which permit the flow of electricity, whereas a sandstone acts much more like an insulator and does not easily permit electricity to flow. Another thing we can do is to look at the natural radioactivity of the rocks, which is usually indicative of the amount of shale or the muddiness of the rock formations. Clay minerals are often rich in these radioactive elements like uranium, thorium, and potassium, so we can use a high gamma log reading as an indicator of shale, whereas a low gamma ray reading may represent something like a sandstone. Of course, we can measure the natural gamma radiation as before, or we can lower a source of gamma rays, like a cesium-137 source down the borehole, which shoots gamma rays at the rocks and essentially counts how many gamma rays are bounced back. The number of scattered gamma rays is related to the electron density of the formation, which depends on the particular chemical composition of the rocks and the density of the rocks. So we can use this measurement to calculate the porosity of the formation, as well as get at things like lithology and density. Another active source geophysical log is the neutron porosity log. We lower a source of high-energy neutrons down the hole, which shoots these neutrons at the side of the borehole. These neutrons collide with hydrogen atoms, which slows them down, and hydrogen atoms are mostly found in fluids, so we can count the slowed neutrons to get an idea of how much fluid there is in the pore spaces of the rock. So really, what we're often doing is sending tools down the hole, which tell us something about the density, the elastic properties, chemical composition, porosity, permeability, and fluid content of these rocks. So these are the observations that we make instead of color or shape of a rock. So now with these brief descriptions of some of the common borehole geophysical logs we collect in a borehole, and remembering that changes in these wireline logs are often due to changes in rock type or fluid content, take a second to pause the video and look at these 3 wireline logs from the San Andreas Fault Observatory at Depth borehole. Try to find the 3 faults that intersect the borehole in this section. There are 2 active strands and 1 extinct strand of the San Andreas Fault here. Pick the depths where you think there are a few faults while I give you a couple seconds. If you need a reminder about what these logs represent, please feel free to go back to their corresponding slide. And okay, I hope you were able to do it. And the 3 fault locations are given here. Each of these faults is associated with some change in the geophysical logs, whether that's a reduction in the seismic wave velocities, or reduction in electrical resistivity, or some change in the natural gamma radiation. And if you choose different depths where you thought there might have been a fault, then all's not lost, since there are absolutely more changes in rock type than just these 3. So take a second again to pause the video, try to spot some places where you think the rock type changed in the borehole aside from at these faults. Okay, I hope you're able to spot the changes in lithology given here. We can see some of the same principles as we discussed before, with the sandstones having higher resistivity than shales, for example. And so take a second to look through this and see if you find anything that surprises you. I mean, this is how we study the modern day San Andreas Fault, so take a second to be excited about this. Pick out some things that you think are fun, and thank you for listening.